All right, so where were we? We were getting into number of signals. So it says the number of signals in a proton NMR spectrum tells you about the number of different kinds of protons in a compound. So let's say you have a compound that has two different types of protons, you're going to see two signals. If you have four different types of protons, you'll have four signals, etc. And sometimes in compounds, we have protons that are chemically equivalent. And when you have protons that are chemically equivalent, they fall into one of two categories. They can either be homotopic or enantiotopic. And so now what we're going to cover is homotopic and enantiotopic protons and how to identify them. So the first one is homotopic. It says if a molecule has an axis of rotational symmetry that allows one proton to be rotated onto the other proton without changing the molecule, we say that they're homotopic. Okay, so if you look at these two protons that I have highlighted in red here, if you were to draw an axis through the molecule like this, if you were to rotate this molecule 180 degrees, so let's say you were looking at the molecule, you closed your eyes, you rotated it 180 degrees, you would not be able to tell that this molecule has been rotated, right? And so we would say that you have a rotational plane here, right? You can rotate or rotational symmetry, and we would say that those protons are homotopic. Now, the next one's a little bit more difficult to tell, but what they're trying to show you here is, let's say you have something that looks like this, where you have this proton here. So you've got the fluorine coming out towards you, right? And then you've got the chlorine in the back. They just kind of turned it to the side. So if you looked at it, all you would see, right, all you would see is the fluorine going straight up like this, but you know that the chlorine is behind it, right, immediately behind it. And so the same thing applies here, or sorry, it's not a chlorine, it's a fluorine. So you can clearly see then that there's a fluorine behind it, right? So you have an axis, right, of rotational symmetry. If you were looking at this molecule and then close your eyes and you rotated it 180 degrees and then opened your eyes, you would not be able to tell that this molecule has been moved. And so we say these two protons are homotopic. And the same thing with cyclopropane. Again, we see that there's an axis running through the molecule this way. If you were looking at the molecule, again, closed your eyes and rotated it 180 degrees and opened your eyes, you would not be able to tell that this molecule has moved in any way. And so we say that these protons are homotopic. So to review, homotopic protons exist when you have an axis of rotational symmetry. Give me a thumbs up if you follow me on that. Rotational symmetry, homotopic protons. Okay, cool. Awesome. All right. So another test. If you're really unsure about the rotational test, you can always do what we call the replacement test, which is where you replace one of the protons for a deuterium and vice versa. So if you replace one hydrogen for a deuterium, and then you replace the other hydrogen with a deuterium, and you end up getting the same compound, then they're homotopic. Okay, that's the replacement test. Usually students can identify the axis of rotational symmetry pretty quickly. In most compounds, they'll just say, well, if I rotate this 180 degrees, I get the same compound. And so I have an axis of rotational symmetry. But we know that rotational symmetry is not the only form of symmetry we can have in an organic compound. We can also have reflectional symmetry, or reflectional symmetry, or we can say that the mirror image is identical on both sides of the compound. So this is what I was getting at the last time. I was actually way ahead of myself. I said, if you take this compound here and you imagine what it looks like if you look at it straight on, right? So you'd have a bond like this and a bond like this. Then you have the fluorine coming out towards you like this, and the chlorine is in the back. Okay, so there's obviously an axis here of reflectional symmetry on either side of the molecule. Give me a thumbs up if you can see that. Is everybody with me on the axis of reflectional symmetry? Okay, cool. Because, yeah, it might be helpful to make a model if you don't see it. But the same thing here with 1-methylcyclopropene, right? We can see that you could slice the molecule right down the middle, and you end up with the same mirror image on both sides. Somebody said, so only the protons need to be symmetrical. So that's what we're talking about, right? Because when we run an NMR spectrum, we're either going to look at proton nuclei or carbon nuclei, right? We're not talking about any other kinds of nuclei, just proton and carbon. Does that make sense? Okay, all right, good. So if you are able to determine whether there's a plane of reflection, or I should say a plane of symmetry in the compound, then you can also do the replacement test. And if you do the replacement test, again, replace one hydrogen with a deuterium, and then replace the other hydrogen with a deuterium. And if you get a pair of enantiomers, then we say that the two protons are enantiotopic. All right. And so what are we getting at here is if you have protons that are homotopic or enantiotopic, they're chemically equivalent. That means they're going to be in the exact same electronic environment, and they're going to absorb at the same frequency, or they're going to have the exact same chemical shift, is what we would say. So what you want to do is you want to look for rotational symmetry. If you don't find rotational symmetry, then you look for a plane of symmetry. So again, this is where you're going to start. You're going to start with your molecule and ask yourself, is there an axis of rotational symmetry? If there is, then the protons are homotopic. If there isn't, then what you do is you look for a plane of symmetry, right? A mirror plane of symmetry. And if there is one, then they are enantiotopic. If neither of those work, they're not chemically equivalent. But again, if you have an axis of rotational symmetry, or if you have a plane of reflectional symmetry, the protons are either homotopic or enantiotopic, and they are chemically equivalent. So if they're chemically equivalent, they have the same chemical shift. All right, same chemical shift. All right, so if you do the replacement test and you get not a pair of enantiomers, or not the same compound, but you get a pair of diastereomers, then the protons are what we say diastereotopic, and they are not chemically equivalent. Okay, so if you do the replacement test, you get a pair of diastereomers, they're diastereotopic, and they're not chemically equivalent. And I can prove that to you very quickly. If you were to look at this compound right here, and you're wondering about these two protons, are they chemically equivalent or not? Well, you can see that this proton here that I'm going to circle in blue, okay, if you imagine yourself as being this proton, you look straight up and you see this hydroxyl, okay? But if you imagine yourself being this proton over here that I have the red circle around, if you look straight up, you do not see a hydroxyl, you see a proton. You have to look over and to the left. And so it's clear that those two protons are in different electronic environments, so they're not chemically equivalent. But again, if you're unsure, you can always do the replacement test, and it will work without fail. So the replacement test is your friend. Now, when we have protons that are diastereotopic, or we can say they're not homotopic or enantiotopic, they're not chemically equivalent. We could do the same thing with this compound here. So this is R2-butanol, okay? So this is an R stereocenter here, right? We go 1, 2, 3, right? So it's going clockwise, so it's R. So we have a stereocenter in the compound, so there's no axis of rotational symmetry. There's no plane of reflectional symmetry. If you imagine yourself being this proton, the one that I have the red circle around, the hydroxyl is on the same face of the molecule as you. And if you imagine yourself as being this proton, okay, the hydroxyl is on the opposite face of the molecule from you. So it's clear again that these are not chemically equivalent, right? And you could also do the replacement test. I'm not going to do it right now, but if you did, in this case, you would end up with a pair of diastereomers. So again, it is clear that they are not chemically equivalent to one another. The protons can't be exchanged by rotational or reflectional symmetry in this case. So the book even says you don't have to drive yourself crazy looking for all kinds of axes and planes of symmetry. There's some shortcuts you can take to determine whether protons are chemically equivalent or not. Here we go. So the first one, I'm not even sure if it's in here. Yeah, so, okay. So I'll do it in the order that they're listed here. So here are the shortcuts. Okay, the first one is 2 protons in a methylene. So remember a CH2, we call that a methylene, right? CH3 is a methyl, CH2 is a methylene. So 2 protons in a methylene are going to be equivalent, end of story, if there's no chiral centers in a molecule. So that would be shown right here. Here you have a methylene. Those 2 protons are chemically equivalent because there's no stereocenters anywhere in that molecule. If you're wondering, are these 2 protons chemically equivalent? That's a methylene, and there's no stereocenters. The answer is yes. Same thing with this methylene here. Okay, so that's the first rule. Second rule is if you've got 2 protons in a methylene and there is a chiral center in the molecule, they're not chemically equivalent, end of story. So if we go over to this molecule, here we have a methylene, CH2, but we have a chiral center in the molecule. They are not chemically equivalent. You can clearly see that this proton is on the same face of the molecule as the hydroxyl, and the other proton is on the opposite face of the hydroxyl. So those are not in the same electronic environment. Ergo, they are not chemically equivalent. No need to even do the replacement test. You just remember rule number 2. Next rule is probably the rule they should have put first in my mind, which is if you have a methyl group, CH3, you know that if you have a methyl group, there's going to be free rotation around that bond, right? If we draw a methyl group, CH3, you draw this proton coming out and this proton going in back. Well, whenever you have a methyl group, there's got to be free rotation around it. And so there's no differentiation, or there's no difference between any of the 3 protons in a methyl group. They're always chemically equivalent to each other. No exceptions to that rule. Always equivalent to each other, all 3 protons in a methyl. And then it says multiple protons on multiple carbons can be equivalent if they can be interchanged through a plane of rotation or an axis of rotation or a plane of reflection. So if you look at this molecule here, this is called 3-pentanone. The name isn't important, but if you look at the molecule, you can clearly see that there is an axis of rotational symmetry, right, going through the molecule if you were to rotate that 180 degrees, but there's also a plane of symmetry all the way through the molecule. And so all 4 of these methylene protons are chemically equivalent. And so they're all chemically equivalent. They're going to give you 1 signal. And if you're looking at it and going, well, the 2 methyl groups, those are chemically equivalent too, aren't they? Because there's rotational symmetry and reflectional symmetry. And the answer is absolutely. Absolutely. All right. And so you have to practice looking at compounds and saying, well, are these protons going to be chemically equivalent or not? And that leads us to one of our good buddies that we studied a lot of in chapter 4, which is the cyclohexane chair. Who remembers this compound? I know you do. And we talked about axial positions and equatorial positions. So if you have the compound cyclohexane, right, which is C6H12, you might look at the chair conformation of this compound and say, well, I've got 2 different types of protons. I've got the axial protons and the equatorial protons. They're not in the exact same electronic environment. And that's actually not that crazy of a train of thought. That's why it's in the textbook. But it turns out that when you run the NMR spectrum on cyclohexane, you only get 1 signal. Okay. Now, why would that be? It's because we know that at room temperature, the chairs are going to interconvert very rapidly. And so it's just like a camera. If you have a person running really fast, the picture is going to come out blurry. And it's the same way with the NMR spectrometer. It's not fast enough to see the individual chair conformations. And so you're going to end up seeing just 1 signal. You see an average of the 2 axial and equatorial positions. You would have to cool the compound all the way down to minus 100 degrees Celsius to see the axial and equatorial protons. So that's something we would never worry about in our class. We're going to run all of our compounds at room temperature. Okay, everything is going to be done at room temperature. And so we would not be able to tell the difference between the axial and the equatorial protons. So with all that in mind, let's take a look at a practice problem and see if we can identify some homotopic and antiotopic or diastereotopic protons. So we'll start out with this first one here. This compound is called anisole. I don't think I've asked you to memorize the name of this compound, but this is called anisole. You could call it methoxybenzene, but anisole is the common name of it. Could anybody tell me, is there an axis of rotational symmetry in anisole? Is there an axis of rotational symmetry in this compound? Yay or nay? Absolutely. Thanks, Hannah. Yeah, sometimes students will get this one wrong, but there totally is, right? And if you make the molecular model of this compound, you can see that you have a methyl group, right, attached here. I kind of don't have it here. Let me just move this a little bit down like this, right? There's your methoxy group. And then you have this proton in red and this proton in red. But this enables you to see that there's clearly an axis of rotational symmetry. And so these 2 protons are going to be homotopic. Homotopic. Isn't that a store at the mall? No, that's hot topic. Sorry, I mixed that up. Anyhow, so if we look at the 2 protons in the next compound, okay, is there an axis of rotational symmetry for B? Is there an axis of rotational symmetry? Yeah, thanks, Sarah. Yeah, the answer is no. Is there a plane of reflectional symmetry? Is there a plane, a mirror plane running all the way through the middle of this thing? The answer is yes. There is a mirror plane in this compound. Yes. So plane of symmetry. And so we would say that these two protons are, again, homotopic. All right. So with that one, we have a plane of symmetry. And again, if you don't want to, if you're like unsure about that, what you could do is you could make, you could do the replacement test, right? We could draw this compound like this, okay? Put this over here and this over here like this. So what I'll do is I'll copy this and put it over here, okay? We'll put a deuterium here, oops, put a deuterium here and a deuterium here and a hydrogen here and a hydrogen here. And you can see that those are enantiomers of each other, right? These two compounds are enantiomers. And so because of that, the protons are enantiotopic and therefore they're chemically equivalent. Does that make more sense now? Okay, awesome, awesome. There we go. And for the last one, we have a methylene. Okay, so we have a methylene here. This is a CH2, but we have a chiral center. So chiral center. So what would be the relationship between the protons here? If we have a methylene and we have a chiral center, they must be diastereotopic. So diastereotopic. And again, you could do the replacement test. And if you do that, you'd see that you would end up with a pair of diastereomers. So there you go. We've covered homotopic, enantiotopic, and diastereotopic. Any questions about that before we move forward? No, definitely. So somebody's asking me if you were a proton here. No, because this is an sp2 hybridized carbon, right? So this is sp2. Therefore, that molecular geometry is trigonal planar. Right? The chlorine is in the plane of the screen or the page. Yeah. There we go. Cool. All right, let's move on to the next question. This is 15.5. Identify the number of signals expected in the proton NMR spectrum. I'm going to kind of guide you through this one a little bit. I'm going to start by, I don't know, what could we do here? We could start with this methyl group on the methoxy, okay? Are there any other protons that are chemically equivalent to these in the compound? Well, obviously not, because there's no other 3 protons attached to a oxygen. So those are unique protons. All right. If I highlight this methyl group in yellow and this methyl group in green, my question to you is, are those 2 methyl groups chemically equivalent, yes or no? And it's not a trick question. This one isn't designed to fool you or anything. Are those 2 methyl groups chemically equivalent? Okay, so the answer is no, okay? Because if we were to rotate this molecule 180 degrees, right, you would be able to tell that the molecule has rotated around, right? You'd end up with this. So you'd end up with this ethyl group here, this ethyl group here, and then OME like that. Okay, so it doesn't have an axis of rotational symmetry. All right, so those are not chemically equivalent. All right, and you can see that they have a different relationship to the oxygen. Right, if you count the number of atoms, so if you go 1, 2, 3, 4, 5 atoms away from the oxygen, and for the one in green, you go 1, 2, 3, 4, 5, 6 atoms away from the oxygen. So now does it make more sense that these are not chemically equivalent? Everybody with me on that? These are not chemically equivalent to each other. Okay, there we go. So, all right. So those are not chemically equivalent to each other. The protons on the methyl individually are chemically equivalent, but these 2 methyl groups are not chemically equivalent. So far we've got 3 types of unique protons. Now, if I highlight this methylene in red and this methylene in blue, are those 2 methylenes chemically equivalent, yes or no? Do they have the same relationship to the oxygen in the methoxy group? No, exactly. So those are not chemically equivalent. We also have 3 more protons in the molecule, don't we? We have a proton, we have a proton here, right? And we have a proton here, and we have a proton here. And none of those protons are chemically equivalent to each other either. And so I'll just erase those right now. But we have unique protons here, here, and here. So if we tally that up, we get a total of 1, 2, 3, 4, 5, 6, 7, 8. There are 8 signals in this compound. So 8 unique sets of protons in this compound. Let me move this next one over here. So if I just redraw it like this, okay, I've got a methyl group down here. I've got an oxygen here, and then I've got a methyl group attached to it like that. This is B. Okay, I'm just solving it over here. I just drew it a different way. So if I highlight this methyl group in yellow and this methyl group in green, are those two methyl groups chemically equivalent? Yes or no? Are they in the same environment? No, absolutely not. So they are both unique. If I highlight this proton, so we've got 4 protons on the aromatic ring, is there an axis of rotational symmetry in this molecule? Is there an axis of rotational symmetry running through this molecule? Yes, absolutely. And so what that means is it means that these 2 protons are going to be chemically equivalent, and these 2 protons are going to be chemically equivalent. And so I have a total of 4 signals for this compound. 4 signals. Give me a thumbs up if that makes sense to you. 4 signals. All right. So let me redraw the last compound. This is called paraxylene. Name is not important, but I have CH3 here and a methyl group over here. So you can see that you've got an axis of rotational symmetry going through the molecule this way, and you also have an axis of rotational symmetry going through the molecule this way. So could anybody tell me how many types of unique protons are there in this molecule? Could anybody just answer the question? Exactly, there's 2. Thanks, Ariana. Because the 2 methyl groups are chemically equivalent, and then all 4 of the aromatic protons, they are all chemically equivalent. And so we have 2 signals for this compound. 2 signals. All right. So remember, each signal gets a unique chemical shift. So now what we're going to do is we're going to switch gears, and we're going to talk, which you have to shift to get to a different gear. And we're going to cover a chemical shift. And it just turns out that in most NMR solvents, they put 1% of this compound called TMS, which stands for tetramethylsilane. So this is tetramethylsilane. And this is just a standard that NMR spectroscopists put in their sample. And the reason why we put this compound, TMS, in most of our samples is because it's got a frequency of absorbance that's lower than most the protons in most organic compounds. And so since different spectroscopists or different spectrometers are going to use magnets with different operating frequencies, what we do is we measure the chemical shift with respect to TMS, or tetramethylsilane, in hertz, and then we divide that by the operating frequency of the spectrometer. So let's say you're using a 300 megahertz instrument. If you do that and you measure the frequency of absorption of some protons in benzene, okay, and benzene only has 1 type of proton. So this is a benzene molecule here, right? So all 6 of the protons are chemically equivalent. So there's only 1 signal, okay? If you measure the absorption frequency of those protons in a 300 megahertz spectrometer, they have an absorbance of 2,181 hertz, okay? But you divide that by the operating frequency of the spectrometer, and you get 7.7 times 10 to the negative 6. You're wondering, what's the relevance of this number here? Well, let's take a look. What if you have another spectrometer that's a 60 megahertz instrument and you run the same NMR for the same compound? So this is for benzene as well. What you get then is that the chemical shift, or the the chemical shift with respect to TMS in a 60 megahertz spectrometer is only 436 hertz. Over here, it was 2181. It's the exact same compound. So if one person owns a 300 megahertz instrument and the other person owns a 60 megahertz instrument, comparing their results, 436 and 2181, that's going to be a huge pain in the neck. What if Eric has a spectrometer that's 500 megahertz and Sarah's got one that's 700 megahertz and I've got a 250? then none of us can compare our results. So what you always do is you divide by the operating frequency of the spectrometer and look at the numbers that we get. They're identical. 7.27 times 10 to the negative 6. So it doesn't matter what spectrometer you're using, you always divide by the field strength, and that or the operating frequency, I should say, and that gives you the same number. So you can compare your relative absorbances. Now you're probably looking at it and saying, well, hertz and hertz cancel, so this is a number that has no units. It's dimensionless, and you'd be absolutely right on that. And so what we do is we say the chemical shift, and this is the little symbol, which is delta. We use this for chemical shift. We use a Greek delta. We just give that number in parts per million. So we multiply it by a million. And so instead of 7.27 times 10 to the negative 6, you would say 7.27 ppm, parts per million. Same thing here. You would say 7.27 parts per million, right? That's all we do, all right, to make things really simple. And for most spectra that we're going to look at, the frequency, the signals are going to appear somewhere between, it says 0 and 10. Let's correct that. It should be 0 and 12 parts per million. So if you have your notes out, change that to 0 to 12 is where most of our signals come out. So just a little bit of history here. And this is kind of annoying to explain to you because it's historical, but sometimes things from history stick around, and you'll find that organic chemistry is largely, or has many examples of this. But the first, so do you remember going back to section 15.2? I told you that we take a sample and we irradiate it with all relevant frequencies of radio waves, okay? And so we said we excite every proton from alpha to beta, and then when they relax, then we record the FID, we do the Fourier transform, and we get our spectrum. The old spectrometers, instead of pulsing the sample with all frequencies of electromagnetic radiation that were relevant, what it did is it only had one frequency of electromagnetic radiation, and what it did is it varied the field strength. So they changed the strength of the magnet. Now it's the opposite. The magnet is constant, and they irradiate it with all frequencies. So historically, what happened was, when you had de-shielded protons, it took less of the magnetic field to get them to come into resonance. And so we call that downfield. And then if you had shielded protons, we call that upfield. But anyhow, so when you have a low field strength is downfield, high field strength is upfield. So it says shielded protons require a stronger magnetic field to be excited as the de-shielded protons. And so, yeah, that's really all there is to it. And even though we don't do that, this is called a continuous wave spectrum. We don't use these anymore, but the terms have stuck around. And so if I say downfield, I mean this direction. And if I say upfield, I mean this direction. Cool. You just kind of have to know it. But after you've looked at enough spectra, you start to get used to talking about downfield and upfield. All right. So again, the current NMRs analyze samples at a constant field strength, right? And then we vary the frequency of electromagnetic radiation. So if you have a proton that's de-shielded, there's a bigger energy gap. And so that's going to be a higher energy. So the de-shielded protons are higher energy. So higher energy is going to be more de-shielded. So that's downfield. And then lower energy is going to be more shielded. Anyhow, there you go. So it gives you a little bit of history. And if you're wondering, have you ever seen one of those old spectrometers? The answer is yes. Where I did my undergraduate, they had one of these. Again, if you want to Google it, it's called a continuous wave spectrometer. And when I was an undergraduate, they actually let us use it. And I think it's because they didn't care if it got broken or not. So they're like, oh, let the students play with it. And we used to run spectra on it. And it wasn't the greatest instrument in the world, but hey, we could get some useful information about it. So let's go back to this idea of chemical shift. We've talked about unique protons, and when protons are homotopic and an antiotopic, they're chemically equivalent. Then we said diastereotopic, they're not chemically equivalent, so they give you different chemical shifts. But what are the numbers that go along with chemical shift for a compound? And it says here for alkane protons, they're generally going to give you a signal of around 1 to 2 parts per million, so somewhere in that neighborhood. But we can shift the protons downfield if we have some kind of electronegative or electron withdrawing atom near our proton. So if we look at the simplest possible organic compound on the planet Earth, that's methane. Methane has a chemical shift of around 1 part per million, but you can see that as we start adding halogens, whether it's an iodine or a bromine or a chlorine or a fluorine, that you know the electronegativity increases, right, going up into the right in the periodic table. So fluorine is the most electronegative. It's got the most de-shielding effect, right, because it's pulling electron density away like crazy, right? It's got a huge dipole, whereas iodine has a small dipole. And so you can see that effect manifest in the chemical shift. The greater the electron withdrawing effect, the greater the de-shielding, and so the higher the absorbance. We can also see that the effect is additive. If you look at this example right here, you can see that if you have one chlorine, it affects the chemical shift by 2.1. If you have two chlorines, it keeps going up, and then three chlorines, it shifts it even more. Now, if you're wondering, well, all of these halogens that you're showing me on this slide, like every single one of them is alpha or next door to the halogen. That's true. So if you're wondering, well, how far can that effect go? Well, if you look at this compound here, so this is 1-chloropropane, you see the de-shielding effect on the alpha protons and the beta protons only. You do not see any effect on gamma carbon. So we only see this de-shielding effect on alpha and beta protons. All right, and for beta protons, it's about one-fifth the effect of the alpha protons. That's not very pretty. Of alpha protons. And I'll show you a table that will help clear that up in just a second here. So to predict a chemical shift, what we do is we use a baseline for a methyl, a methylene, and a methine, and you have to memorize these. Okay, so the baseline for a methyl is always 0.9 parts per million. The baseline for a methylene, so a methyl is a CH3, a methylene is a CH2, so the baseline for a methylene is 1.2 parts per million. And a methine, that's a CH group. Okay, the baseline for a methine is 1.7. And then we use table 15.1 to adjust the chemical shift depending on the proximity to certain functional groups. So I would ask you to memorize this table. Table 15.1, you must memorize this table. So let's take a look. If you have protons that are alpha to an oxygen of an alcohol or an ether, what it does is it increases the chemical shift by 2.5 parts per million. Okay, why is that? Because oxygen is the second most electronegative element in the periodic table, right? Fluorine gets the gold, and we always remember fluorine, but just remember, people, oxygen gets the silver medal. Okay, it comes in second place in the entire periodic table. So oxygen is very electron withdrawing. And so let's say you have an oxygen next to these two methylene protons, okay? So the baseline of a methylene, we said, was 1.2, okay? And then the electron withdrawing effect of this oxygen is 2.5. So we add 2.5 to 1.2, and we get a chemical shift of 3.7. It turns out the actual chemical shift is 3.7. The same thing, it says here, if you have an oxygen of an ester, and this is the oxygen of an ester, okay, if you have protons next to the oxygen of the ester, this is a really powerful electron withdrawing effect. It's +3 parts per million. And so let's say you have your methylene, which has a baseline of 1.2. You would add 3 to that, and that gives you 4.2. Remember, what's highlighted in green here is an estimation. The actual chemical shift is 4.1, so you can see it's very, very close. Now, again, it says the effect of beta protons is about 1/5 the effect of alpha protons. So let me show you how you would calculate this. I'll use ethanol. So the example that they have here, I'll try to draw it the exact same way he has it here. So he has this, okay? So we've already covered these two protons, okay? And we said that they had a chemical shift, an estimate of about 3.7 ppm. So these are the alpha protons, right? This is the beta carbon, and this has a methyl group on it, right? CH3. So what would be the chemical shift of these? The baseline of a methyl was 0.9 parts per million. Go back to the previous slide. And now you're going to add 1/5 of this effect. So if you take 2.5 and you divide it by 5, you get 0.5. So 1/5 of the effect is 0.5 ppm. We tally those up and we get an estimation of 1.4 parts per million for those 3 beta protons. Give me a thumbs up if you follow me on the beta protons thing. Right, okay. So 1/5 of 2.5 is 0.5. What's 1/5 of 3, Eric? What's 1/5 of 3 for anybody? 0.6, right? So if you take 3 divided by 5, you get 0.6 ppm. So this is the beta effect. There we go. Thanks, Hannah. And the last one is if you have protons that are alpha to a carbonyl group. So in the carbonyl could be from a ketone, aldehyde, ester, whatever. Okay. Well, for that effect, you add 1. Okay. So you have alpha protons that are next to this carbonyl. So your methylene baseline is 1.2. You add 1, you get 2.2. The actual chemical shift is 2.4. So you see the prediction is really good. If we were to do, a prediction for the methyl protons, 1, 2, 3, right? What you would say is the baseline is 0.9 parts per million. And 1/5 of 1, right? Because this is a beta carbon. 1/5 of 1 is 0.2. And you would tally those up and you would get 1.1 ppm. All right, there you go. And it says here handbooks or tables can be found online and at credible websites and can be used for functional groups beyond this table. So before we end lecture today, I'm going to show you a table that I will allow you to bring into quiz 15. Okay, so there's a table of proton NMR shifts that I will allow you to bring into the quiz. So you don't have to have them all perfectly memorized, but you should be relatively accustomed to knowing what chemical shifts are. Why? Because there's no table given to you for the final exam. And if you take any other standardized exam on organic chemistry, there will not be any table provided. All right, let's take a look at one more topic here, which is diamagnetic anisotropy. We'll do a problem on chemical shifts, and then we'll take another break before we tackle integration and multiplicity. So check this out. This is a really neat effect that you need to know about. It's called diamagnetic anisotropy. It says if you have a pi system, so that means an aromatic ring, right? If you have an aromatic ring, you know how we draw the aromatic ring like this with all 3 pi bonds? You can also draw an aromatic ring like this with a circle inside to show that all of those pi electrons are being shared because you have a continuously overlapping system of p orbitals in an aromatic ring. So what happens is when the electrons in a pi system are subjected to B0, that externally applied magnetic field, they circle around and they produce a magnetic field. But check this out. If you look at the ring, so if this is your aromatic ring right here, so I'll highlight it in yellow, there's the aromatic ring. What do you notice? Look at this. So if you're not paying attention, start to wake up, but I know you're all paying attention. But look at this. The field lines inside the ring are going against the magnetic field, okay? But check this out. I'll highlight it in green. The field lines going on the outside are opposite. They're going along with the externally applied magnetic field. Well, where are the protons in an aromatic ring? They're on the outside, okay? And so what ends up happening to the aromatic protons is they feel not only B0, but they feel this magnetic field that was made by the circulation of the electrons in the aromatic ring, the pi electrons. So now they have this like huge magnetic field acting on them. And so what does that do? It creates this crazy de-shielding effect on aromatic protons. So what happens is that the regions outside the ring have an increased magnetic field, and that leads to a real extreme de-shielding effect. So the result of diamagnetic anisotropy is similar to de-shielding. And so what happens is that aromatic protons usually have an absorbance of somewhere around 7 to 8 parts per million. They have a really high chemical shift because of that diamagnetic anisotropy, the magnetic field created by the pi electrons in the ring. So it takes more energy to spin flip them, so they absorb at a higher frequency and have a higher chemical shift. It says here 7 parts per million. That's probably close enough for our class, but it's usually in between 7 and 8 parts per million. And another thing that's interesting is even if the protons are close to the ring, so you see you have methylene protons here, and we said the baseline of a methylene was 1.2. Well, I'll just tell you that those methylene protons are represented by this quartet right here. And look at the absorbance. It's 2.61 or something like that. And the reason why the chemical shift is way higher than the expected 1.2, it's because even though the protons are like further away than the CH2 protons are further away than the red protons, they still experience some of the effect. It drops off as you get further away, but it's a pretty cool effect, diamagnetic anisotropy. Now, if you're wondering about chemical shifts for other functional groups, I just happen to have this table. So what I'm going to give you again for quiz 1 is some version of this table, But instead of memorize, I'll put familiarize yourself with this table and memorize for the final. Memorize for final exam. And we'll say familiarize for quiz. Okay, because I'll allow you to bring this table or a version of this table. It won't look exactly like this. But for the quiz, and again, you can't print this slide out. I give you a table, okay, and I'll show it to you later on today. But we assume that by the final exam that you know the chemical shift. So let's take a look at them. We've already covered methyl, methylene, and methine. So those are all in the bag. Next is allylic proton. So if you have an sp2 hybridized carbon, you go one carbon away, and this one is sp3. The hydrogens that are attached to it have a chemical shift of around 2. An alkyne, terminal alkyne, so this hydrogen has a chemical shift of around 2.5. And you saw the aromatic protons on the previous slide were pretty close to 2.5, weren't they? They came out around 2.61, so very, very close. So aromatic methyl is around 2.5. Alkyl halide, we just studied this a few slides ago, right? Because the X can be equal to fluorine, chlorine, bromine, or iodine. And so we see a huge range. It's from 2 to 5, or sorry, from 2 to 4. Also, alcohols have a huge, huge range from 2 to 5, which is pretty big. And there's a good reason for that we'll talk about later on. Vinylic protons, so those are the ones attached to an sp2 hybridized carbon. They're around 4.5 to 6.5. And if you have aromatic protons, those are around 6.5 to 8. Right? I said 7 to 8, which is still close, okay? Ones that are easier to remember are aldehyde. The only thing that we ever see that comes out at 10 parts per million is an aldehyde. And the only thing we ever see that comes out at 12 is a carboxylic acid. So usually if you have a signal at 10 or 12, you can figure it out right away. This is an aldehyde or this is a carboxylic acid. All right, so those are the chemical shifts that you are going to need to know. So with all that in mind, let's see if we can calculate some chemical shifts. So what I think we'll do is we'll do the first one as a group, then we'll take a short break, and we're going to see if you guys can determine the chemical shifts of the next one. So let's start with the aldehyde proton here. And we know that an aldehyde proton has a chemical shift of around 10 parts per million. So we'll put here aldehyde. So this is going to have a chemical shift close to 10 parts per million. Next, we'll do these two protons. I'll just circle it in blue, maybe. There we go. So these protons, that's a methylene. Now, a methylene has a baseline of 1.2, but those are not just any old methylene, are they? This is an allylic methylene. So allylic, right? Remember, you have sp2, and then you have an sp3 next to it. That's an allylic position. So these are allylic. So their baseline is going to be 2, right? Because if we go back here, we said the baseline for allylic was 2, all right? And then they're alpha to a carbonyl. So if they're alpha to a carbonyl, we have to add 1, right? Because this is the alpha position or next door to a carbonyl, and I'm getting that from this table right here, right? Those protons are next door to a carbonyl. So let's go back to the question. Zoink, here we go. So we're going to add 1, and we end up with 3 parts per million. That's our guess, right? That's what we think it is, okay? This one here, this is a vinylic proton. It's attached to an sp2 hybridized carbon, so this is vinylic. And we said that vinylic protons had a chemical shift of 4.5 to 6.5, so vinylic is 4.5 to 6.5 ppm. But these ones are beta to a carbonyl, and a carbonyl had effect of 1, but if it's beta to it, it's going to be a fifth of that. So you could change this to 4.7 to 6.7, right? Because a fifth of 1 is 0.2. So we'll put here 4.7 to 6.7. I think the textbook just says 4.5 to 6.5. I think they didn't add the 0.2 because it's such a huge variation, so they just kind of said the hell with it. This next one here, this is an allylic proton. So allylic, a vinylic proton again. So vinylic has a chemical shift of around, we'll put here vinylic. So we'll put here 4.5 to 6.5. It's not beta to anything. The next one is allylic. So these two are allylic, and they're not beta to anything electron withdrawing. And so we say that allylic protons have a chemical shift of around 2 parts per million. I'll put here 2 ppm. Let's see, then we have a methylene here. So this methylene, there's nothing exciting about this. It's not alpha or beta to anything. So we'll just put here methylene. So that's going to have a baseline of about 1.2 parts per million. And then the last one is this proton here, which is an alkyne proton. We said that has a chemical shift of around 2.5. So alkyne has a chemical shift of around 2.5 parts per million. And there you go. We figured out an estimation of all the chemical shifts. So for this compound here, we've got 2 protons here. Okay, those are both vinylic. Then we have 3 allylic protons here. Okay, so we've got those ones. We have these methylene protons. We have these methylene protons. And then we have the hydrogen of the hydroxyl. That didn't come out very well. So what we're going to do now is we're going to take a short break, and I would like everybody to try to figure out what's the chemical shift of these protons, what's the chemical shift of these protons, what's the chemical shift of these protons, what's the chemical shift for these 3 protons, and what is the chemical shift for this guy. So there's what, 1, 2, 3, 4, 5 chemical shifts I'd like you to try to determine before we come back.